Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so hello everyone. So it's a pleasure today to have Benjamin Pierce from the University of Pennsylvania with us. Benjamin has worked on many topics ranging from types in programming languages to differential privacy to testing to security and information flow enforcing and synchronization. And Benjamin, it's all yours now. Thanks.
Thank you. Okay, thanks everybody for waking up and coming. I'd like to tell you, as Dimitri said, about work we're doing lately at Penn on a thing we call micropolicies. I won't spend long on motivation because I don't think anybody would disagree in this room that where we are at the moment with respect to security of software systems is not where we want to be. A more interesting question is how we got there, and of course there are many answers. But one that I think is interesting is the fact that we're still, in some ways, really living with legacy hardware and software decisions that were made for perfectly good reasons quite a long time ago, when hardware was extremely expensive, when our ability to specify and verify systems was very limited, and when, frankly, security really didn't matter all that much. And the result of those design decisions, reasonable at the time, was systems with very poor hardware abstractions and a very high cost to isolating system components and protecting them from each other. But in the meantime, a lot has changed in the world. In particular, security is a lot more important, and hardware is a lot cheaper. So we believe that it's time to reconsider the trade-off calculus and see if there isn't a way to spend some of the abundant hardware resources that we have now on getting better security at the lowest levels of systems. And of course, this is not an idea that's unique to us, but we have a particular take on it, which I'll tell you about. So to be more specific, what we'd like is to find a way of making hardware better at enforcing invariance of higher levels of the system. And of course, to do that, we need a way of communicating those invariants to the hardware. One way to communicate invariants to hardware is to build them in. But of course, being a programming languages kind of guy, I would rather have a more flexible solution. And so we work with an idea called micropolicies, which sounds to Simon very governmental, but in fact is a fairly technical notion. So what I mean by micropolicies is a fairly diverse collection of instruction-level enforcement mechanisms of policies that can be phrased in terms of metadata on the data that's flowing through the system. And we have a particular notion of a particular subset of those that we know how to accelerate in hardware. And it will be those I'll be telling you about. So if we succeed in doing this, the win, of course, is that we now have programmable hardware that can support low level of enforcement of a wide range of policies. We're able to experiment with using those policy enforcement mechanisms to harden and protect the very lowest levels of software in systems, and we have opportunities for safety interlocks protection at multiple levels. So we have not built all of these micropolicies. We're experimenting with a few of them, but just to give you a sense of what we believe might be the range of things that one could address in a micropolicy framework, Here are a bunch of things that we think are promising things to experiment with, and we've actually experimented with 5 or 6 of them, and I'll show you those today. So to tell you a little bit about where this came from, some of you may know that that for the last several years we at Penn have been engaged in a big DARPA project called Crash Safe, where the goal there was to completely redesign the whole hardware-software stack. It was an extremely ambitious kind of let's do something impossible sort of project, and at both hardware and software levels of the system, there were many interesting innovations, which I would love to tell you about another time. But what we're doing now, and the goal of the present effort is more focused. It's to take just one of those mechanisms, this particular way of propagating and checking metadata, to extract that from the crash safe design and to transplant it into a more conventional hardware-software setting. So we're thinking now of extending a conventional instruction set and processor design, and we're also generalizing at the same time the information flow policy that we concentrated on in the SAFE project to a wider range of policies, including information flow, among many others. So where are we now? We're kind of in the middle of all of this, so we don't have final results to show. We have, I hope, interesting and suggestive intermediate results. So what we have is prototype implementations of several micropolicies, including those plus information flow. We have simulation experiments using a simulated alpha processor plus supporting hardware and software to get some idea of the performance and energy and area and power impact of these extensions. And we have a detailed formalization of simplified versions of some of these things that gives us a sense of what it means for it to work. So what I'd like to do today is...
Your kind of ultimate hope is to persuade the likes of Intel that actually they should use some of their abundant transistors to do something like this.
That is what we would like to do.
Uh-huh. But that's the only feasible path to impact.
Yes.
Right.
Well, fortunately, not just Intel. There are a large handful of places that you might have impact in that way, but that ARM. But that is the ultimate goal. At the moment, the crash system runs on FPGAs, so you could imagine just distributing it that way. But for really wide impact, you would want to get some big manufacturer interested. We're a couple of design generations off from that being an appropriate direct target. So here's the structure of the talk, but I'm showing you this now so that you can kind of think about which part you're going to be most interested in peppering me with questions about. Thank you, Simon, for breaking the ice. And we can really concentrate on whichever of these interests people. So let me tell you a little bit about the hardware, because this gives kind of grounds it in the reality of what sorts of policies we can hope to accelerate effectively, and then look at the policies themselves. So here's the idea. We call it the PUMP, the Programmable Unit for Metadata Processing. And what we do is, so we begin, as I said, with a conventional ISA like an alpha. We add to every word everywhere in the system. So in registers, in caches, in memory, the program counter, every place there's a word of data. There will now also be a word size bundle of metadata. Why word size? Because that's big enough to hold a pointer. And that means that the size of metadata structures that you can represent is effectively unbounded. So as far as the hardware is concerned, at the level of the acceleration mechanism, these tags are going to be just bits. But at the level of software, when we are instructing the hardware what to do, we can choose any interpretation we like. either encoding the information that we have, if it's just a little bit, directly in the tag bits, or letting the tag be a pointer to some larger structure in memory. Okay, so we add a lot of tag bits to each word. Of course, this is a conceptual model, and in the implementation, we may play lots of tricks. But for present purposes, let's think of it that way. These tagged words are going to be indivisible atoms in the user's view of operating the machine. And at the hardware level, what's going to happen is on each instruction dispatch, we're going to pull off the tags from all of the relevant bits of the current machine state. So we're going to take the tag on the current instruction and the tag on the program counter and the tag on any registers that are being used and the tag on the memory location that's being used if there is one. We're going to take all of those tags and look them up in a hardware rule cache that will give us back, if the lookup succeeds, will give us back the next tag for the program counter and the next tag for the result of the operation, if there was one, in the machine state that results from this step. Is that a question?
Yes. So about application or software view of the tagging.
Yep.
By atomic indivisible, do you mean completely opaque, or is
as far as user level software is concerned, the tags are completely opaque and not directly accessible.
Operating system?
As far as the operating system is concerned, well, there's a question about to what extent you want to consider the operating system to be above the tagging mechanism, and to what extent it needs to be in bed with the tagging mechanism. So there's a little bit of operating system code, which I'll show you in more detail in a few slides, that handles misses in the rule cache. And that, of course, needs direct access to the tag. So it uses some privileged instructions that let it directly read and write the tags. But the intention is that nowhere else in the system, even in the lowest levels of the rest of the operating system, are the tags directly accessible. Okay. So this is just pictorially what I just said. So here's a conventional processor diagram, and here it is extended with extra tag stuff, and everything gets pulled off as the instruction gets decoded and stuffed through the, we usually call it pump now, but it used to be called tag management unit, stuffed through that, and then the results are recombined as things come back around out of the ALU.
So why doesn't the iStore have this green?
Oh, it probably should. Okay, and I'm not going to go into the microarchitecture beyond this slide, partly because it's not really what I want to talk about today, and partly because it's really other people's domain to figure that stuff out. But the basic idea is that we need to add just one pipeline stage. So this is a standard, simple 5-stage pipeline. And we just add one stage at the end that does the lookup in the rule cache and combines the result with the results coming out of the earlier stages.
I thought you were going to tell us you had 0 stages, but it's done in parallel. Why do you need to add a stage at all?
Well,
And while the ALU is computing, you're calculating the new tag.
yeah, but we need, okay, now we get to subtleties that I may not be able to answer correctly, but we need information from all of the previous stages, including potentially the memory that we're writing into, for example, the destination memory. For things like information flow, where you need to be careful about things like sensitive upgrades of memory that you're writing to. Yeah, so that, yeah, please.
Are you concerned for the fact that you're putting the pump, or in some cases you have to put the pump in the end because you have to read the memory, as you said. But in other cases, maybe you want to do the pump early. So were other performance issues and kind of, how often you have to kind of flush your pipelines and how many things you have to flush in the pipeline if you put the pump in the beginning or in the end?
Undoubtedly. So I can't speak to them because it's not even my student, it's my colleague's student that's actually doing that work. if you are interested in that level, there is going to be a forthcoming paper about pipelining. Okay, so here's a simple example of how it might work. So up there is the Up there is the software, down here is the hardware. This is the ALU, not shown because it's standard. And here is the pump. Here's the rule cache. And then down there are some ground rules, which I'm not going to talk about right now, but I'll come back to later on. So let's say we're enforcing a very, very simple information flow policy. We have just two tags, secret and public. And the user code is doing some arithmetic. So in the rule cache, we have two rules. One says if you add a public thing to a public thing, the result is a public thing. And I'm suppressing some of the fields of the rules in the full system. We would also take the tag from the PC and return a new tag from the PC, as I said. But this is a simplified version. So it says if we're adding two public things, then the result is a public thing. And if we're adding two secret things, the result is a secret thing. So completely unsurprising rules. Now what happens? When we're executing the first add instruction, we pull off those tags and send them over to the pump while the ALU is doing its thing. So in this case, suppose both arguments were secret. Well, then the pump sends back the result secret. That gets recombined with the added bits and stuck onto register R3. Another thing that can happen is that we ask a question that the rule cache doesn't know the answer to. So we ask, suppose R1 is public and R4 is secret. Well now we're going to miss in the cache and trap to a software service routine whose job is to consult a symbolic representation of the policy, which says when you're trying to add two things labeled L1 and L2, and those are symbolic labels, then the result, the label of the result, should be the join of L1 and L2. So that gets installed in the cache as a new rule, and we restart the instruction that trapped. Now, when we ask the question, we get back the answer directly from the cache. Okay, and of course, as I said, we need to have a tag on the PC also to track implicit flows, and the fact that we're using word size tags means that we can represent much richer flavors of label. For example, if we wanted to have dynamically generated principles and have tags be sets of principles that are expressing an interest in the confidentiality of the data, then we would just make the tag be a pointer to a data structure representing a set. And then at the symbolic level, we would need to do operations like set, union, and subset, and so on. But at the concrete hardware level, we're still just comparing bit patterns. George?
How can you prevent the PC from being permanently tainted?
I'm sorry?
How can you prevent the PC from being permanently tainted?
So this is a question for the policy designer. And that may take us too far afield to answer it in detail. One way to do it, without giving a full answer, one way to do it is to just let the PC drift up continually and make sure that you fork a new process for doing computations where you want the PC to go up without tainting the main computation. So that's what they do in the LIO system, for example. In the safe processor, we use a different thing where we identify merge points in the control flow graph, like returning from subroutines, and allow the PC to go down then. So there are a variety of policies that can work for information flow at the hardware level, and the intention is that this mechanism be able to encode all of them.
Do you have special instructions that are devoted only to sort of triggering some policy shift on the program counter, say, without doing any interesting computation per se?
No, but I'll get to this in a second. We have two ways of doing that. So one is that each micropolicy comes along with some system services that can be called from user programs. So it has a sort of hardware-facing part that handles traps, and it has a software-facing part that does things like, in an information flow policy, please create me a new principal, can this label flow to that one, and so on.
Right.
So that's one way of doing it. Another way of doing it is you can make up, you can tag instructions with special tags. So for example, you could have a move instruction, or indeed a no-op instruction, tagged with a special tag that means something to the rule system. And if there isn't a rule for it in the cache, then you're just going to trap when you see it, and now you can do anything you want. Okay, let's look at a few more details of micropolicies. So as I said, answering Simon, a micropolicy really has three parts. It has a set of tags that we're going to use for labeling things. It has a set of rules for propagating those labels. And it has a set of monitor services or system calls that can be made from user code down into the micropolicy for performing more global operations involving tags. And we'll see examples of all of those shortly. When we write down the rules at the symbolic level, we often write them with notations like this. So a symbolic policy is convenient to represent as just a list of rules of this form that basically just match on the opcode and the tags of a bunch of things and return new tags, and might have a Boolean expression saying when the operation is allowed. If it isn't allowed, then of course when a trap happens, the trap service routine is not going to install a new rule. Instead, it's going to inform the scheduler that this process needs to be killed.
Speaking of the scheduler, when you have multiple processes, do you need to flush out the rule cache every time?
So no. And the reason again is that we have that our tags can represent pointers to anything. So in a multiprocessing setting, what we would probably do if we wanted to have many processes with different policies, we might have one policy enforced throughout the system. But if different policies if we wanted to enforce different policies in different processes, all we need to do is add a process ID. Is to make the tag be a tuple of the process ID and some tag relevant to the policy that's being enforced by that process. Of course, doing that increases the pressure on the rule cache. And as you might guess, pressure on the rule cache is the main thing that determines the performance of the system that you get. Okay. So here's a really simple policy, dynamic ceiling. So the tags in this policy are, there's an infinite collection of tags, or a really large collection of tags. There's data. So data is the tag that we use for most things. Then we have tags sealed k, which means this is a data value that's been sealed with a key k. And shouldn't be readable by anyone that doesn't possess that key. So it's a kind of linguistic hardware accelerated cryptography, if you want. And then the other kind of tag is key k, and we use this tag to represent keys. So a key k is represented as a value that we don't care about, say 0, tagged key of k. And now the rules, let's jump down here. The rules look like this. The instructions that just move data around, like store, are going to insist that the PC not be a key or a sealed thing. So the PC has to be just data, and the instruction that we're executing has to be just data. But the source register can be tagged anything. And the result, the memory location that we store into, is going to be tagged the same at the end of the operation. Okay, so data movement instructions just preserve tags, while data manipulation instructions, like jump through a value, are going to insist that that value is also data. Then for the monitor services, we're going to need something to generate a key. So new key is a system call, a kernel call that can be made from user code, and it makes up a fresh key k that no one has ever seen before, and returns 0 tagged with key of k. And then seal takes 2 arguments in 2 registers, one tagged v not sealed, and the other tagged, we don't care what the value is, tagged key of k, and it returns v tagged sealed of k, and then unsealed just does the converse.
So silly question. So would this architecture allow an actual cryptographic implementation?
The architecture doesn't directly allow it and doesn't need it. But of course, if you wanted, you could add more monitor services for converting between the sealed representation and a cryptographically protected representation. And indeed, you would want that if you wanted to, say, put these sealed things out on external storage. But there's some system design to do to. I'm waving my hands here. To make that really work would not be completely simple.
And the thing that's trusted here is the combination of the hardware, the rules, and the monitor service.
Precisely.
So, and the monitor service presumably is, and indeed the fault handlers, are presumably all operating in some other instruction set that can do all manner of crazy stuff with tags without any checking at all.
Almost. So I have slides on this in a minute, but let me address it now. So you might ask yourself, as Simon is, what about all of this code that's manipulating all of these tags directly? Doesn't it have to be ultra super trusted? And the answer is yes, it does. Because if that code is wrong or goes wrong, then absolutely nothing else in the system can be trusted. So it has to be right. So how do we protect it? 2 ways. First, it's ordinary code, and in the simple design that we have at the moment, we just have a flat address space with no protection other than tags. So the protection on that code, like the protection on everything else, is just tags. So in a little bit more detail, there's a special distinguished tag, which we call kernel. And its bit pattern is known and agreed on in advance and known to the hardware. So when we take a trap because of a miss in the rule cache, we set the tag of the PC to 0, which means kernel. Now we come back to these ground rules that I mentioned at the beginning. So in the rule cache, at boot time, or perhaps at hardware fab time, we install a set of rules involving the kernel tag, which are then never evicted. They're permanently in the cache. And they say things like, if the PC says kernel and the instruction that we're executing says kernel, then it's okay to execute it and the PC stays kernel. We are very careful, very, very careful, not to put rules in the cache that say things like, if the PC is tagged something other than kernel and the instruction is tagged kernel, then it can proceed and here's the result. So the protection of kernel code and data structures is a result of our care not to put rules ever in the cache that allow user code to do kernel things. And of course, okay, so that's the mechanism. Now, how are we sure that the mechanism works? We prove it. So that's a sufficiently critical mechanism and a sufficiently small amount of mechanism that it really warrants a proof, and we've done one. Okay, let's go on. Here's another policy. This one is a simple version of control flow integrity. So the idea here is that we're going to use the tag on the PC and on instructions. We're not really going to tag data in an interesting way to track the progress of control flow through the program. So the tags are basically just addresses of instructions or any other set of large set of tags. And the scheme is we ask the compiler to please dump out the control flow graph along with the binary of the program. And while loading the process, we tag control flow endpoints with these unique identifiers, and we remember the correspondence between those identifiers and edges in the control flow graph. Okay, so if you think of those identifiers as addresses, then the control flow graph is pairs of addresses that are allowed to branch from X to Y. And the tags on those addresses say, this is X or that's Y. Now, the rules say on a branch instruction, on a control flow transfer, we take the tag on the current instruction and put it in the PC, put it in the PC tag. Then on the next instruction, then we just execute the branch. On the next instruction, we notice, the rules notice, that the PC is tagged something other than the default. Namely, we just branched from someplace. And we check that the tag on the current instruction, together with the tag on the PC, is an allowed pair in the control flow graph. So the contents of the rule cache are essentially the recently seen subset of the control flow graph edges.
This is going to be a bit tricky in programs which roll into chunks.
Um,
You might be able to predict a priori in your static control flow.
Indeed. So this, like other kinds of control flow integrity, this analysis is only as good as the compiler's control flow graph.
Right. And the compiler control flow graph might be legitimately not very good.
Might be legitimately not very good.
Right.
So. Here's another one. We can do memory protection using tags. So the scheme is every time you call malloc, malloc generates a fresh tag. So malloc becomes part of the policy. So malloc generates a fresh tag and tags all of the memory locations in the block that it's returning you and the pointer that it's returning you with this tag. Now, when you're loading and storing, you have to check that the tag on the pointer is the same as the tag on the location that you're loading and storing into or from. There's one tricky subtlety, which I'll say before George points it out, which is that when you store a pointer into memory, you actually have two tags now, one on the memory location and one on the pointer itself. So in fact, the tags that we use in this scheme are really pairs of, or the tags on memory rather, are pairs of the tag on the memory contents and the tag on the memory location, conceptually. A similar scheme can be used to do compartmentalization. So the idea here is that memory is divided up into a set of compartments. Each compartment has a tag, which is chosen at the moment that that compartment is created. And each compartment has a set of addresses in other compartments that it's allowed to jump to and another set that it's allowed to write to. So this scheme is similar to the design of the original software fault isolation system, except that, of course, we're not doing it with binary rewriting. We're doing it in hardware. And so the way it works is like this. So at any given moment, the PC is tagged to indicate which compartment we're in. And each memory location is tagged to represent, here's the interesting thing, not the compartment that it's in, but the set of compartments that are allowed to jump to it and the set of compartments that are allowed to write to it. So these jump and write tables are kind of dualized in the tag representation. Now on each read and write, on each write and one instruction after each branch, like in the CFI, we compare the PC tag with the tag on the memory location that we're doing something with and see if that's an okay step. And then for monitor services, we of course need a new compartment call that splits the current compartment. Okay. I've already talked about this, so let me skip over it and tell you a little bit about the architecture of the proofs that we've done. So as I said at the beginning, we have we have many things in various stages of completion. For the safe processor, we have running hardware on FPGAs. For the alpha plus pump, we have instruction level simulations and performance estimates. And for a simplified version of each of those, we have quite a bit of proofs. So what do we want to prove? Well, first of all, we want to prove that this kernel protection scheme that protects that uses tags to protect the tag hardware and software is correct. And then for each micro policy, we want to know that it's correct in the sense that both it preserves the invariants that are needed by the kernel protection and that it correctly realizes whatever specification we've decided it should have. So the way that we think about it is this: there's some generic parts, and then there's some policy-specific parts. On the generic side, we have, of course, the hardware itself. We have a generic part of the trap handler for rule cache misses that does the low-level fiddling with hardware, and then invokes the policy-specific part. And we also have a symbolic machine, which is a middle layer of abstraction between the very most concrete machine running a particular policy and the very abstract machine that we intend that policy to realize. Okay. In practice, what do? We have an implementation of a policy which is some machine code that needs to get run when services are called or when the rule cache traps. We install that on the concrete hardware, and now we want to. What we would like is that running user programs on that machine with system software installed behaves like a machine that has, say, compartmentalization built in. So way up here, there's an abstract compartmentalization machine with a primitive for compartment creation that divides up the memory and whatnot. And then in the middle, to make thinking about it easier, we have this symbolic machine, which consists of a machine definition whose execution model is executing these symbolic rules that I showed you a few slides ago. And then on the policy design side, we provide not just the machine code, but also a symbolic representation of the policy itself. Now, ultimately, that machine code is going to be generated from the symbolic policy by a little compiler. And for one specific policy, information flow, we have written that compiler. But for the more interesting, more general policy language that we're dealing with now, we have not finished that step. So, the monitor code here and the symbolic policy are connected by a proof, either a one-off proof that you implemented the policy correctly, or a once and for all correctness proof of the compiler that takes these symbolic rules and generates the code, whichever you like. Then you have for each policy your abstract specification that says, this is my compartmentalization machine that programmers are going to think in terms of at the user level. And what we want is a proof that this concrete machine running that concrete code implements that policy. And we've carried out that proof. We just submitted a paper a few weeks ago to a conference that you can probably guess. We just carrying out that exercise for compartmentalization, memory safety, sealing, and CFI, so for a range of micropolicies. And that included quite a bit of proof engineering to make as much as possible of this and this refinement proof generic. Please.
It's generic in terms of what? In terms of the monitor code or in terms of the general enforcement of the monitor code?
I'm not certain what distinction you're making. So can you ask again?
I'm just asking what is the generality of this refinement that you mentioned?
For example, the main generic bit of proof that we have is a generic proof that the concrete machine running any policy monitor satisfies the corresponding symbolic machine under some quite specific assumptions about the relation between this code and this code. Okay, I think I've said this already.
One more question.
Yes, please. Sorry.
Abstract machine. That's a contradiction in terms. Let me give you an example. One of the ways I might specify an abstract policy would be to say it respects ownership of data by threads.
Mm-hmm.
So and it doesn't have any null references, and it doesn't overflow any buffers or other arrays.
Mm-hmm.
That seems to be at the sort of level of abstraction that one could say it was really abstract. Have you got any examples of that?
Sort of. So this is something we've thought about quite a bit in the process of doing this this last round of formalization experiments. What is an appropriate specification for some policy? It really depends a lot on the policy. So for example, for memory safety, you can write down an abstract machine, and it really is a machine, that is self-evidently memory safe because its memory model is segmented. So every single pointer has two parts, a segment part and an offset within the segment. And you just, by construction, can't run off the end of a segment. We've tried to think about what would be an even higher level specification of memory safety than that, and it's hard to come up with one. So for memory safety, that seems like a perfectly good and adequate specification of what memory safety is. You're providing a machine to the programmer where you self-evidently can't overflow a buffer. For other policies, like information flow, there are much higher level properties that you can enunciate and reason about. So what we did in that experiment was to say, okay, here is an information flow machine. So we had an abstract machine. It had built-in labels, information flow labels, in the style of information flow calculi that you've seen. But then we proved some properties of that machine. Directly at the level of that abstract machine, we proved that it has a non-interference property. Or in the case of the compartmentalization machine, we prove that the compartments are isolated. Or in the case of the control flow integrity policy, we prove that the abstract machine, that the steps of the abstract machine necessarily follow the given control flow graph. And then we need to check that those properties are preserved by the refinements all the way down the stack so that they become properties of the code running on the concrete machine. Okay. Let me tell you in 3 minutes about the most important, at a conceptual level, open problem, which is the issue of composition. And this is what we're really struggling with right now. So I've described a bunch of individual policies. And they are probably individually quite useful, but really, one would like to have memory safety and control flow integrity. And yes, let's have some dynamic sealing too. So for certain combinations of policies, just kind of whacking them together and running them in parallel is perfectly reasonable. So for example, memory safety together with control flow integrity, you don't really need to do anything. You just observe that since tags can be pointers to tuples of other tags, you can just say, well, the policy is the pair of the CFI and the memory safety policy, and you do everything pointwise. And when you're propagating tags, you just run the separate policies. And when you're checking whether an operation is OK, if either policy says no, then you say no. And it's as simple as that. So that kind of composition is straightforward, and we've built things like that and measured them and so on.
I mean, it's not entirely straightforward because it has an interesting compilation problem, I suppose. Or maybe merging the tags or something, because you don't want big paying cost, going to some direction that has a tuple of the policies.
Yeah, that's true. If it comes to making really high performance versions, then.
But it has no logical. It has no
right.
logical complexity.
Right. At the conceptual level, it's easy to see what it's done. And actually, it's the conceptual level that's the hardest, because even when the policies themselves are not orthogonal, you can still the implementation aspect of whacking them together is easy. You just have to ask yourself, well, what did that mean when I did that? So what's an example of non-orthogonal? So memory safety and compartmentalization both have system calls that need to deal with large blocks of memory. So the memory safety policy has malloc as a system call that's part of the policy. And it has to tag the new memory with its memory tag. And then the compartmentalization policy needs to know what compartment that new memory is in. So it's going to need to put tags on the memory also. So if you just try to think of them as completely separate things, it just doesn't work. So what should you do? We're not sure, but we have a couple of ideas. One possibility, the last point on the slide, is maybe instead of thinking of composing things in parallel, we should think of composing them in series, somewhat in the style of Haskell monad transformers. So you don't just assume that you can, with monads, you just don't assume that you can take two monads and whack them together and everything is going to work. One might need to be wrapped around the other in a way that the ordering matters. And indeed, where the outer one might need to know about the inner one and do things with its special primitives. So similarly here, maybe memory allocation is a really special thing and needs to live at the very bottom of a stack of policies that are organized in layers. Another possibility is, what if at least some operations were not part of policies? This is, in a way, an instantiation of the same idea. What if operations like memory allocation were not things that were provided by policies, but were provided by the policy framework? So we say, well, memory allocation is a really special thing, and policies are going to need to deal with it as part of their view of the underlying machine. So rather than programming the monitor services, the system calls, directly on the hardware, we program them on an abstraction of the hardware that includes things like memory allocation and perhaps key allocation as primitive. Okay, so these are ideas that we're experimenting with. I don't know which are going to work. Let me quickly tell you a little bit about what we know about what we can see at this point about how this thing is going to perform. Because obviously, doing hardware-accelerated security is only fun if it's fast enough. So to get a sense of that, we built a simulation of an alpha processor plus pump hardware and low-level software and all that, and tested it with the Spec 2006 benchmark suite using an orthogonal composite, so a memory safety plus CFI plus a simple kind of taint tracking to see what would happen. So here is the runtime overhead, and here are all the individual policies broken down into where the time is going. And the interesting one is the geometric mean over there, which is around 8%, I think. So in the 8 to 10% range. So this is the amount of overhead that we're adding to the runtime of these benchmarks. Quite a bit of this overhead is fixed. So even the null policy takes, I forget, 7 or 8% overhead.
Is that the extra pipeline?
And this is the extra pipeline stage, and making various things slow down just a tiny bit, making reducing the size of the L1 and L2 caches because we need some of it for the rule cache, and so on, and adding tag words everywhere. For energy, again, looking at the geometric mean, we're in the 60% or so overhead range. And this is after some amount of pretty hard work on crunching things down. But I think it's far from all we can do. So this is kind of one paper worth of effort on optimizing the microarchitecture. So this news is a little bit less good than the performance, but I think in the ballpark that we want it. And then the absolute power is actually not bad. So namely, this graph is showing the white parts are the baseline alpha architecture, not extended with the pump. And then the colored parts are the with pump running all of these policies. And you can see that there are some where the pump extended one is pretty expensive in terms of power ceiling, but the unextended one was pretty expensive too. So the amount of power that we're adding is reasonable in most cases. Area is the place where we have not extensively optimized. In fact, some of the energy and runtime optimizations are bad for area, and so there we're at around 110% overhead. Although again, especially for external memory, there are lots of known optimization techniques for crunching these things down. Okay, so let me finish up. I don't think I want to take your time to go through all of this in detail, but at the hardware level, there are many competing attempts to do various sorts of tagging in hardware. Ours is the only one where the number of tag bits, because we can indirect through the tag, is effectively unbounded. But there are a lot of things that there are a lot of previous systems that share other properties with us. And I'd be happy to give you a draft paper that talks about this in more detail.
You haven't quite mentioned explicitly that in addition to using transistors that you might argue are readily available on the CPU, you're also using double the number of transistors in the memory. That is,
Yes.
every byte you store now is another byte of tag associated.
Yes,
with it.
so in the optimized microarchitecture, it's not quite so bad.
I'm just thinking memory. Right, if you need 2 gigabytes of memory before, now you need 4. Isn't that right?
So there's, let me distinguish between on-chip and off-chip memory.
Yeah, I'm thinking of off-chip.
Okay, so for off-chip memory, that's where things like this Mondrian memory can apply. So we have not yet investigated optimizing off-chip memory, but lots of people have experimented with schemes where you can, where if ranges of, to the extent that ranges of memory are tagged homogeneously, you can represent things very much more compactly at some cost in complexity and performance.
Which might or might not be the case.
Which might or might not be the case depending on the policy.
Yeah.
And indeed, as I mentioned before, the really critical question here that we're just getting to the point of being able to seriously answer is, what are the working set sizes for the kind of composite policies that we want to use for real application programs? And the spec benchmarks give some indication that maybe we're in the right ballpark, but I don't think we should feel convinced yet.
Memory safety is the one where you're most likely to have scattered.
Exactly.
Because an object will have pointers to lots of other objects, and they'll all have different tags.
Exactly. Memory safety is the one that worries me the most.
Okay, and so then your on-chip cache, your level 1, level 2. Now let's talk about on-chip memory. That they would be sort of contain half as much data.
That's right.
Well,
unless you crunch them down, which we do. So that's the part where we have done some optimization. And so one observation, for example, is that if your rule cache is only 4,000 entries, then there's not much point in having the tags in that rule cache be longer than 12 bits. So we do some translation of tags between the long form and the short form. And right. Right. Okay, I think I've mentioned future work sufficiently already. We're defining more policies, building hardware, and there's one thing I haven't mentioned, which is one aspect that we're very interested in that I briefly touched on at the beginning is once you have policy enforcement in the hardware, now you can enforce policies of the operating system. So you don't need to think of the operating system as this monolithic thing that's providing security abstractions to the above layers. You can actually think about compartmentalizing it and enforcing that compartmentalization because the enforcement is light enough weight. And that is something that we're very interested in. So my colleague Andre has this slogan of he wants to build the zero kernel operating system. Now, one has to be a little careful because, of course, the cache management software is always going to be quite sensitive and need to be trusted. But as we've seen, we can hope to do proofs about that. So then the rest of what's usually kernel, one can think about using those facilities for protecting it. Okay, and that brings me to the end. Thank you very much for your attention and questions. Cedric?
So for many individual policies, you could either use the new hardware or you could do binary rewriting. And the overhead would be, at least for some policies, quite comparable. So I'm wondering if you have a characterization of what are good policies for rewriting, what are policies that really require hardware, and if there is, what are the perspectives of having a hybrid approach where you try to remove everything that is complicated and have something that is.
Yeah, I don't have a really good characterization, but two things that might make you lean toward a hardware implementation are there are some situations where binary rewriting depends on static analysis of the binary that's hard. And there might be some situations where your binaries are going to be interacting with unknown binaries, and so you want protection at a lower level. So, but these are just thoughts. We don't have really results about that. I'm sorry.
So yes, so that's the advantage of forcing everyone to comply with the policy.
Indeed.
Because it's in hardware, but
Yep.
okay.
So just very related to this question, if you have could you go to the slide with the performance for spec, the CPU performance?
Sorry, which slide?
The CPU performance results for
Yeah.
So do you have these numbers for the sign policies but excluding time tracking? Because time tracking seems the only expensive thing you are doing here. The rest you can implement very efficiently in software.
As Simon pointed out, memory safety can be. Oh no, sorry. You mean there are efficient software implementations?
Yes.
Yes, we do have the numbers broken out. I don't remember them off the cuff.
Yeah, because I mean, memory safety and CFI, you would get software implementations that are better than this.
Yep.
And so Benjamin's going to be here for the rest of the day. I think he has meetings until 2 or 3, but after that, I think his schedule is free. So if you want to talk to him and you're not scheduled already, please let me know. And thanks very much.
Okay, thank you.